Hello everyone, my name is Wang, and I'm a first-year PhD student at the University of Queensland, under the supervision of Professor Guangdong Bai and Dr. Minghui Xue. Today I'm excited to present our work, CoreLocker, Neuron Level Usage Control. This is a joint work with Sarah Study 61 and the University of Adelaide. In recent days, creating a successful deep neural network often takes a lot of resources. They need tons of high-quality data, a lot of computational power, and sophisticated architectural design. For example, GPT-3 has 175 billion parameters and requires 355 GPU years and $4.6 million just for a single training run. For the model owner, the payoff of such investments can be huge. Take ChatGPT. It attracted 100 million active users within 2 months of its launch, and earns $80 million per month for OpenAI. This makes DNNs incredibly valuable intellectual property, highlighting the importance of protecting and monetizing these assets. To monetize these models effectively, a common way is to deploy them via machine learning as a service or through on-device deployment. Sometimes, a model owner may also offer different versions of models at varying price points at one time, aiming to provide users with greater flexibility. In these situations, as a model isn't directly controlled by the owner, unethical entities might exploit the model for unfair competition or unauthorized subletting, which can lead to financial losses for the model owners. Recently, a study on more than 1,000 mobile apps found that 41% of them failed to secure their DNN models against on-device model inference attacks, raising significant concerns. There exists some potential solution to mitigate this. Some methods embed watermarks or signatures into the DNN models to verify the model ownership, but they often fail to prevent unauthorized usage once the model is exposed, and the incentive for safety remain. Other approaches use parameter encryptions or perturbations to prevent unauthorized use, but these have significant limitations. For example, they require additional training and access to training data. They entail retraining models for each key and each model version, making it extremely time-consuming and unsuitable for pre-trained models. Additionally, they can be detected and removed through out-of-distribution value detection, and their effectiveness lacks theoretical support. Our research aims to address this gap with a training data agnostic and retraining-free approach, which can directly operate on off-the-shelf pre-trained models. Specifically, we aim to answer the research question of how to degrade a model's performance to a lower utility level, while ensuring that the full utility can be efficiently restored by authorized users. Our method, CoreLocker, strategically extracts a small subset of significant weights from the neural network. This subset serves as an access key to unlock the model's complete capability. The extraction of the key can be customized to different levels of utility that the model owner intends to release. Authorized users with the access key have full access to the model, while unauthorized users can only access part of its capability. The key selection methodology here is crucial. As we aim to operate directly on pre-trained models, we focus on the fundamental structural bedrock, the model weights, which determine a neural network's functionality. Our intuition is that the performance of a neural network is largely reliant on a crucial subset of weights. Let's look at the figure on the left, which visualizes all 64 filters from the first convolutional layer of a VGG net, sorted by their L1 norm. This highlight in color indicate that only a small subset of weights are particularly significant. These significant weights seem to capture more input features, as illustrated by the visualization of the feature map of the top and bottom 6 filters. So, if a neural network's performance disproportionately depends on a small subset of critical weights, extracting these weights will likely to incapacitate the network. Such an extraction procedure is illustrated in the animation. Based on this insight, we conduct both theoretical and empirical analysis on our magnitude-based key extraction. Importantly, we provide theoretical bounds that systematically quantify how weight extraction alternations in each layer propagate through the network and manifest in the output layer. This is achieved by bounding the difference of weight matrices of F star and F alpha layer by layer. The established bounds provide a solid theoretical foundation for neuron-level usage control and grant the effectiveness of our approach. Crucially, we established a direct relationship between weight matrices and neural network output disparity. As shown in this animation, we found a clear trend that the disparity between the networks increases rapidly as the extraction ratio increases. This finding is further corroborated by empirical results. Our evaluation across all experimental settings shows that the model accuracy smoothly and consistently decreases with the increase of extraction ratios. Taking this figure as an example, our extraction method degraded the model performance to a random guess level with a mere extraction of around 2%. This implies that CoreLocker can effectively provide model usage control through neuron-level access key extraction, as well as provide granular utility control through customized key volume. Further, this table provides a detailed mapping between the utility range and the extraction ratio of a ResNet and DenseNet model. The consistent result confirms that CoreLocker's usage control capability clearly. By using our method, all model versions can be obtained by applying different extraction ratios to a single model. In practice, the model owner can establish a direct mapping between the extraction ratio and the model utility based on the established theoretical bounds. To ensure that our approach is practical, we tested it on various well-known network architectures, including convolutional networks, recurrent neural networks, and transformers. The results show that our method is broadly applicable based on the key property of impact concentration within neural networks. In summary, we established a crucial research problem of AI model usage control, which requires a neuron-level log of the model's utility while ensuring that its full utility can be efficiently restored for authorized use with an access key. Our work allows the model owner to create a low-utility version of the model that can be fully restored after authorization. While achieving this, our method stands out as lightweight, data-agnostic, retraining-free, universally applicable, and backed by a strong formal foundation. Thanks for your attention. Please refer to our paper for more information.